going to be looking at. First part, energy of chemical reactions. How does this work? Second part, looking at collision theory. Energy of reactions. Quick review here of endo versus exo. Endo versus exo. We talked about this back in Unit 1 a long time ago. Chemical reactions always involve a change in energy. Temperature goes up, temperature goes down. Feel it get warmer, feel it get colder. That's an indication of chemical change. Now, energy is absorbed or released in a chemical reaction. And we have the two types. One type it's being absorbed. The other type it's being released. Chemical reactions are described as endo or exo. Now, paying particular attention to the lovely graphics up here. In the endothermic, what you see here is it starts out, the temperature starts out a lot higher and the temperature decreases. What that actually means from us and from the thermometer's perspective, we are located in the surroundings. The chemical reaction itself is called the system. So we're standing in the surroundings. It feels cold to us and the temperature is going down. Why? Because the surroundings is losing energy and the system is absorbing or gaining that energy. And how heat transfers, heat always transfers from the warmer object to the colder object. So if I put my hand on the board and the board feels cold to me, that's because my hand is warmer and the heat is transferring from my hand into the board. So in this particular case, this reaction requires energy, so it's sucking it from the surroundings, and that's what's making the thermometer go down. So endothermic reactions always feel cold to us because it's taking energy into the bonds when it's creating its new products. Exothermic, though, is the opposite, and you can think of it as exiting. You have your system, which are the chemicals themselves, again, reacting. You have bonds breaking, bonds forming. In that process, though, it releases energy to the surroundings, where the thermometer is and where we are. So we feel the warmth from the reaction. So if it feels warm to us, that means energy in the bonds that were stored in the bonds have left and come to the surroundings. That's why combustion, anything that heats up, is going to be exothermic because we're feeling the warmth of the reaction. We're located in the surroundings. So as you can see, as you add the sodium hydroxide to the hydrochloric, the temperature goes up. Why? Because heat's being released in that process. Now, energy diagrams. We have to know and be able to read them. These are not that hard, though, by the way. Endothermic, once again, with the nice little cold beer that's shivering. Love the Giphies on here. They're great. Energy is absorbed. The system gets cooler. And energy needed. Reactants, heat, or energy is always going to be positioned on the reactant side. It needs to be absorbed so it goes in like a reactant. Now on the energy diagram, they're known as potential energy diagrams or PE diagrams because we're talking about potential energy, energy that is stored in the bonds of the reactants and products. A little bit different than kinetic energy, which would be the energy of motion. You have kind of a few distinct features here on your graph. One of them's the flat line over here. One of them's the flat line over here, and then the hill part, this part. The beginning of the reaction, you have reactants. So this beginning line over here is going to be your reactants. So that's what you want to drop and drag over there. Oh, not reaction, reactants. This is going to be, this line right here represents the energy that's stored in the bonds of the reactants. The reaction happens in the hill part. You have the bond breaking, bond forming, all that stuff going on. Then you end up over here with the amount of energy stored in the bonds of the products. So that second line over to the right is going to be the product energy. So drop and drag that over. What you notice here on the endothermic one is that the product line is higher than the reactant line because energy is being absorbed and going into the product bonds. On the exothermic side here, energy is released, the system gets warmer. Actually, technically the surroundings do, but the energy originally stored in the bonds, okay, heat is being given off as a product. Heat is being on the product side this time because it's being released. So here and here, these designations do not change. This is still the energy in the reactants over here. These are still the energy of the products. The difference is in the endothermic, is that the reactants and products are now switched. The products amount is lower than the reactants amount. That amount of energy difference between them is what's being released from the system to the surroundings. So you see the reactant line is higher than the products, then you know it's exothermic. If you see that the reactant line is lower than the products, you know it's endothermic. That's kind of what you need to be able to read from these graphs. Next part, two other features that you have to label and know what the meaning is on the graph. One of them is called activation energy, EA. Activation energy. And yes, I know, it's a silly abbreviation. It should be AE, but we're going with EA because that's what they told us it is. It is the minimum amount of energy that the reactants need to get started, to get the reaction going. Okay? You need a certain amount of energy to get the reaction going, and that's the activation energy. The way it looks on the graph, you still have your reactants right here. You still have your products right here. If your reactant line is here, you have to get to the top of the hill. That's when the bond breaking and the bond breaking starts here. So this amount here from the top of the hill to the reactant line is going to be your activation energy. So from the reactant line to the top of the hill, the difference there, that amount of energy is how much needs to be added to get it started. What you should notice, the difference, you can drop and drag that. Here on the exothermic side, the reactants and the products, look at the amount of the activation energy here. The activation energy for the exothermic one isn't as high of a hill. It isn't as large. On the endothermic, it's quite a large amount. Most endothermic reactions, not all, but there's a few that are exceptions, but most endothermic reactions, you have to give them heat. You have to heat them up to get them started. The other thing we need to label is something called delta H, or the enthalpy change. The change in enthalpy, better known as delta H. Okay, everybody knows delta is a symbol for change of, right? You've seen that in math and everything. The difference between the energy of the products and reactants. And I'm going to also say that right here too. This is how I write it out. Delta H is the H products minus the H reactants. So the heat of the products minus the heat of the reactants. And it needs to go in that direction because the signs do matter. So, when we're looking here, we have our products, and we have our reactants here, like so. The difference is going to be between these two. This is going to be your delta H. Now, the delta H of the endothermic side. Products are higher than the reactants, so you're going to end up getting a positive delta H here. Because the products are higher, subtract, you're going to get a positive number, numerical value. That's positive. On the other side over here, we're looking here at this, dotted line right here. This case, the products minus the reactants, the delta H is going to be negative. Now, when we get to thermochemistry, we'll probably do a little bit more with this, but the sign pretty much is telling you the direction of the heat flow. Positive delta H means it's being absorbed and added. Negative delta H means it's being released and going out to the surroundings. Okay? But that's how we calculate it, and that's how we label it on these graphs. So let's practice. Go ahead, take a moment, try to fill this in based on that information that you just went over. All right, which letter on the graph indicates the reactants? That would be A. Very good. Definitely A. Which letter on the graph represents the products? B. Thank you. Yes, that would be B. Exactly right. Which letter on the graph indicates the activation energies? Which one's the activation energy? Anyone? Starting at the reactant line, going to the top. Exactly right. Very good. C. Right here from the energy of the reactants to the top of the hill. Now, let's actually read the graph. How much energy is contained in the reactants? Like, what's the numerical value? 10 kilocalories. Very good. Don't forget your unit. Very important. 10 kilocalories. Yes. How about the energy contained in the products? Yes, this is right here. So that goes over here. 20 sounds good to me. 20 kilocalories. Yes. What is the activation energy? This one's kind of tough because it's not particularly lined up, but I'll try my best to dot it over. I mean, what's your best estimate here? What do you guys think? It's about 35, 37-ish. I kind of agree it's a little bit above center, but all right. So let's go with 36. 36 in between. 36. And 10 is the reactant, so minus the 10. This is to get you the activation energy. So let's go with what? 26 kilocalories. There you go. You have to kind of do that difference. Now the enthalpy change. Remember the enthalpy change, or delta H? We're going to do products minus reactants. So products would be 20 minus the reactants here, which would be 10. So what is our delta H? 10 kilocalories, and it happens to be positive 10 kilocalories. Because this one is what type of reaction? Is that endo or exo? I hear endo. Endo sounds right. Why is it endo? How can we tell that this is endo?
Well, it's going up, and then it's like the reaction, like the amount of energy contained in the reaction is more. Oh, the amount of energy in the product is more than the reaction.
Correct. The amount of energy in the products is higher. There's more energy in the products than there are in the beginning with the reactants. That means energy was absorbed into the new bonds. So that one has to be endothermic. Product line higher, endothermic. Product line lower, exothermic. All right, collision theory. And this is my most favorite video of the year, by the way, so I'm just going to tell you. Hopefully you'll enjoy it. But let's go over collision theory, and then I think we have enough time just to pretty much watch the video. All right, collision theory. First thing, in order for a reaction to occur, we have to have molecules, atoms, elements, compounds. They have to hit each other and collide. There will not be any bond breaking or bond forming of new substances without a collision. So here are the postulates basically of collision theory. They have to collide. They have to collide with enough energy, and that energy is the activation energy to get started. And they have to collide at the correct orientation. Now pay attention real quick to these two graphics. The one on the left is showing you incorrect orientation. Why? Because the green or blue circles are coming near each other. And that's not where the new bond is going to form. So they're not hitting in the correct direction. The one on the right, though, as you see, if the molecule with the three blue circles hits the side with the orange, it breaks the bond between the blue circle, and it creates a new bond between the blue and the orange one. So orientation matters. If you don't hit the correct side, it's just going to bounce right off. It's like an elastic collision. So have to collide with enough energy, that's the activation energy, and has to collide in the correct direction, the correct orientation. Now there are ways to speed up a chemical reaction and make them go faster. And this is where we're going to start looking from the video perspective. It's a really great analogy, very fun analogy about how to make a reaction go faster. Okay, so they showed you 5 ways in there, but one of them is actually manipulating the same thing just by 2 different ways, like adding the people versus shrinking the space. So both of those are under the term concentration. All right, so put the link in there. Now, this is the one that was the shrinking of the hallways and also the one where they added more people. Because you can affect concentration. Concentration is a certain amount of molecules in a given amount of space or volume. So as you can see up here, more molecules equals more collisions. This particular diagram shows you higher concentration, lower concentration. They appear to have the same volume because they're the same size squares up there, or rectangles up there. And the one on the left has more of the red dots in there. That would be the chemical. So that one would be more concentrated. Okay? So we designate it, we use something called molarity to determine how concentrated a certain substance is. And it is a calculated numerical value, like down here, this one says 6, this one says 1 molar. Well, the one that has 6 molar is going to be the one that's higher concentrated. Okay. Now, let's finish up with the calculations of the molarity here. Really, molarity is just a measure of the number of moles per liters of solution. So, for instance here, what is the molarity of a solution that contains 0.32 moles of NaCl in 3.4 liters? Well, it's just a simple division. You would put 0.032 moles here over 3.4 liters here. Then you would get out your handy dandy calculator and you would calculate the value. Now here, we still use our significant figures, whereas the top number has 2 significant figures, the bottom number has 2 significant figures, so we would keep 2 in our answer. So here, this is what I would round it to if anybody's interested. This would be 0.094 molar, and you use the big M to represent molarity, which is moles over liters. We will finish the rest on Thursday, but that's a good start for kinetics.